In this video, we'll be learning about parametric equations. Parametric equations can be similar to equations we've done on the Cartesian plane, where we're looking at an xy plane, and we've done a lot with plotting lines on the Cartesian plane. And what we should probably do is review a little bit about the variables we use in this instance. So we usually say that the x-axis or the x-axis variable is the independent variable, and we say that the y-axis is the dependent variable. Another way of thinking about this is if I have a linear equation, I can take any x and use my equation to determine the y. So we think of it as the y depending on the x value. We have many ways of looking at lines, and one of the equations that we like the most is y equals mx plus b. This is just a form of a linear equation where m is the slope of the line and b is the y-intercept. So there's a little refresher on the Cartesian plane, some variables, and linear equations. So let's take a look at a situation where parametric equations come into play. So what if we know how an object moves with respect to time? So on the Cartesian plane, we have a situation where we have an x and a y. They're both talking about position, but there's no time involved. So what if we had a situation like this? What if we had a billiard table, and we're going to take a billiard ball, a pool ball, and let's say we're going to roll it across the table. And let's say we know where we're going to start, time equals 0, and then we're going to roll it across the table and then take snapshots of it at specific intervals. So let's take a look at that. So we'll roll it across the table. Here we go, boom, snapshot at 2 seconds, 4 seconds, and then let's say it stops there after 6 seconds. So we don't really know much about this motion in terms of x and y, but we know that after 2 seconds, it's going to have some position, and after 4 seconds, it's going to have some position, and after 6 seconds, it's going to have some position. So in order to take a closer look at this, let's plop this pool table right down on the Cartesian plane. Let's put it right on a set of axes. There we go. And then we'll say our pool table is marked with distances, so we can measure, okay, we've got 1, 4, 7, and 10. We see some locations on that x-axis, and then 3, 4, 5, and 6 are some locations on the y. So now what we can do is we can take, for every time, we can get an x-coordinate and a y-coordinate. And that coordinate refers specifically to that time. So at 0 seconds, we see we're going to start at 1, 3. 2 seconds later, we're going to be at 4, 4. At 4 seconds, we're going to be at 7, 5. And then finally, when we stop at 6 seconds, we're going to be at 10, 6. So what we want to do is find a way to model the way x behaves with respect to time and the way y behaves with respect to time. So instead of y depending only on x, now what we've got is a situation where y depends on t and x depends on t. And this relationship is independent. Y can have a different relationship. Y can change differently with respect to time than x, as x changes with respect to time. So what we're going to look for is, instead of like a y equals equation, we're going to have a function of position with respect to time. So that's where this p of t comes in. So p is going to stand for position, t, time, is our variable, and we're going to get an ordered pair that's going to be a function of x with respect to time and a function of y with respect to time. So in that ordered pair, our x-coordinate we can find out once we find out how x is behaving with respect to time, and our y-coordinate likewise we can find out once we figure out what's going on. So that's our goal, is to get an expression, an equation of position with respect to time, where time is our only variable, so we can see how this thing is moving as time changes. Okay. So there's our little coordinates. We have to figure out how x behaves with respect to time and how y behaves with respect to time. Okay, so let's start with looking back to what we did at the first slide there, which was our linear equations. So we can make a linear equation for x with respect to time and y with respect to time, where each one has their own slope. I called them m1 and m2, and each one is going to have its own starting point, you can think of it, or the y-intercept. For the y value and the x-intercept for the x value. I like to think of it, it's easier for b1 and b2 to be the starting points for parametrics. So let's go and look at, we'll start with x's. So we need to fill in for what we can in this equation. We need to find m1 and b1 basically, so we can find a linear relationship between x and t. So the best way to start with this is to pick a point. A nice point to start with is at time equals 0. So let's look at when time equals 0. What can we fill in here? Well, we know the point there is 1, 3. So we know when time is 0, the x value is going to be 1. So let's plug that into this equation. So we're going to have 1 is equal to m1 times t, which is 0, plus b1. And an interesting thing happens here. Since time is 0, our m1 term is going to drop out, and we've just solved for b1 in our x term. Okay, now let's take another point. We can pick any of them. For this, I just picked when time is 2. So we know after 2 seconds, we're at 4, 4. So let's do the same thing. We've got that point there, and let's plug it into our linear equation for x. So we're going to get 4 is equal to m1 times 2 plus b1. We just solved for b1 in the previous equation, so I'm just going to put the 1 right in there. So we can do some steps here, subtract 1 from both sides, divide by 2, and we find m1. It's 3/2. So when we put all of this together, we've found our equation for x. We're going to throw our m1 and our b1 in there, and we get x is 3/2 t plus 1. This is how x is changing as time changes. So that's a great relationship to have. All right, let's hold on to that for a second, and now let's find what our y value is going to be, what our y relationship is. So again, we're going to look to fill in the blanks here. We need to fill in m2 and b2. So again, we're going to do the same process. Let's just take time equals 0. So we know we have this point again. Now instead of looking at the x value, we're going to look at the y value this time. So I'm going to start with a 3. So 3 is going to be equal to m2 times the time 0 plus b2. The m term drops out, and we get b2 is equal to 3. Now let's take another point. Again, I picked time is equal to 2. You could pick any point for this. And we've got 4, 4. So I know I'm going to have 4 is equal to m2 times 2 plus my b2, which is 3. So let's subtract 3 from both sides, divide by 2. And our m2 term is going to be 1/2. So now we can put it all together, and we get our nice y with respect to t. So we get y is equal to 1/2 t plus 3. That's how y is behaving as t changes. Okay, so now we've got how x is behaving and how y is behaving. And remember, we were looking for this. We were looking for position with respect to time, and we wanted to see how x and y were changing because we wanted it to be an ordered pair. So we can take our x and our y equations there, and we can throw them right into this position so we can get this nice equation. The position of the ball with respect to time is going to be this ordered pair. So at any specific time, we're at a specific point. So it's going to be an ordered pair. And at any time t, we're going to be at, the x-coordinate is going to be 3/2 t plus 1, and the y-coordinate is going to be 1/2 t plus 3. Okay, so there's our x and there's our y. Excellent. So we can find out where the ball is at any time now with this equation. There we go. So let's do an example here. Let's do another example. Where is the ball after 7 seconds? Well, in order to find this, all I'm going to need to do is plug 7 in for my t there in that equation, and let's see what happens. So I'm going to have p of 7. It's going to be equal to 3/2. My time is 7 again, plus 1. And then 1/2 times 7 plus 3. And we can simplify there. A couple steps here. And we get the position is going to be 11.5, 6.5. And if we look at our diagram, that makes sense, doesn't it? It's going to keep moving to the right, and it's going to move up a little bit. So we're going to be at 11.5, 6.5. So there's an introduction to parametric equations. We can see how the position of something changes as time changes, instead of looking at how y changes as x changes. Okay. So let's check out a different example here. We're going to have a problem where there's two boys, Adam and Ben, and they're playing soccer in a field. So Ben is 10 meters south and 30 meters east of Adam, and Adam's going to kick a soccer ball towards Ben. After 3 seconds, we know the ball is 12 meters east and 4 meters south of Ben, and we want to find out how long it takes the ball to get to Ben. And we're going to use parametric equations, the stuff that we just kind of discovered in that last example, to find the solution. So let's look at a little picture of this. So there's Adam, and there's Ben, and Adam's got his soccer ball, and he's going to kick it all the way over to Ben. There we go. And from the question, we know that they have this relationship as far as position with respect to one another. So we've got that 10 meters and that 30 meters. Okay, so now let's have Adam kick the ball again, and this time we're going to take a snapshot at that 3-second mark where the problem gave us the location. So let's kick the ball again, and after 3 seconds we'll take that nice snapshot. Okay, so that's where that ball is. And let's now put this on the axes like we did before. I'm not going to superimpose them on here again, but let's just say that Adam, where Adam is going to be the origin, okay? So that means with respect to the origin, that 3-second snapshot is going to be at 12 comma negative 4, right? We're moving down, so we'll just keep consistent that down is negative. Okay, so there's where our second point is. And we know that at 0 seconds, we're going to be at the origin, so we're going to be at 0, 0. And then we'll just throw that 3-second point in there, 12, negative 4. So let's set up some parametric equations. We know we want to have the x is a function of time. So let's take that first point and plug it into the same thing we did in that previous example. So we're going to have 0 is m1 times 0 plus b1, right? So the m1 is going to cancel out, and we're going to have b1 is equal to 0. Okay, that's nice. So now let's plug in that 3-second point. So 12 is going to be m1 times 3 plus our b1, which is 0. So m1 is 4. Nice. There's our equation for x. It's a little simpler this time. Starting at the origin, it turns out, makes things a little nicer because we're starting at 0 instead of a different point. So our b terms are going to be 0. So x is 4t. So whatever t is, x is going to be 4 times its size. All right? Now we can go through and do the same exact thing with y. Let's start with that first point. Time is 0 at 0, 0. Okay, we plug in 0. We find b2 is 0. We were expecting that. That's good. Now let's look at the second point. So our y value is negative 4. So we have negative 4 is equal to m2 times 3 plus 0. So m2 is negative 4/3. And our y equation with respect to t is negative 4/3 t. Excellent. Okay. So let's go and put that together. There's our position function. So position with respect to time is going to be 4t comma negative 4/3 t. All right. So we still need to find out how long it's going to take to get to Ben. So Ben's position, if Adam is at the origin, is going to be 30 comma negative 10 because we're going to the right 30 and down 10. So we have two ways of solving this time. One is we can plug 30 in for the x value, right? Because we know we want the time when the x value is 30. And the other way is to plug negative 10 in for the y value and solve for t, because we expect at whatever time we get to negative 10, we're going to be at Ben as well. So these two ways should result in the same answer, and let's do both just to be sure. So first I'm going to plug in to that t value. Remember, when we get to Ben, that x value there should be 30. So I'm going to set 4t equal to 30. We can do a quick little algebra step here and get 7.5 seconds for t. Okay, not too bad. The next one looks a little more complicated, but I don't think it's going to be too bad. So we're going to set up negative 4/3 t is equal to negative 10. Remember, we want that y value to be negative 10. And let's solve for t here. We're going to multiply both sides by 3, and let's divide by a negative 4. And we'll simplify, and we get 7.5 seconds. Excellent. That's good. That means that p of 7.5 is going to be 30 comma negative 10. So that tells us it's going to take 7.5 seconds for the ball to get all the way to Ben. All right. So what if I asked a different question? What if I asked where the ball is after 5 seconds? Well, this should be a little easier because all we're going to need to do is plug 5 into our position function, right? We know the time, so let's do that. There we go. P of 5 is going to be 4 times 5, comma, minus 4/3 times 5. So we're going to get 20, comma, negative 20/3. And that's going to be somewhere right around here, right? So negative 20/3 is almost negative 7. So we're going to be definitely over to the right more and down, right on our way to 30, negative 10. So there's another parametric equation example. And one thing I wanted to throw right in the end here, just as a little teaser of how cool parametrics can be. When you look at it with these linear equations, they're very useful, but they're not very exciting. Once we get a little further and we start looking at trig functions in parametrics, we can graph some really cool things. So this nasty thing down here, P of t is equal to 3 cos 3t times cosine t, comma, cosine 3t sine t. It looks nasty, but watch what happens when we graph this and as time changes. We get a cool flower. And we can make a bunch of different petals on this flower by manipulating this graph, and we can do a lot of cool things. So parametrics are really interesting, and we just started getting our feet wet with linear parametric equations, but hopefully you've seen how they can be useful in certain situations, and they have great utility in the math world.